Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The genesis of a new mathematical field often arises from a single, transformative insight, a reframing of a classical problem that reveals structures previously unseen. The discipline of probabilistic number theory, a profound synthesis of the discrete and the continuous, finds its definitive origin in the 1939 paper by Paul Erdös and Mark Kac, which reached publication in 1940, while the name of Alfred Rényi is inextricably linked with Erdös through their extensive later collaborations that deepened and expanded this very field. The foundational document belongs to the singular partnership of Erdös and Kac. This essay will undertake a rigorous, section-by-section evaluation of the internal claims, mechanisms, and arguments presented within that seminal work. The purpose is to dissect the intellectual architecture of their proof, assessing the validity and ingenuity of its components as they were originally articulated. The paper's central achievement was to demonstrate that a fundamental property of integers, their composition from prime factors, conforms with breathtaking precision to the Gaussian normal distribution, the bell curve that governs so many phenomena of chance. This inquiry will illuminate how their argument forged an unbreakable link between the rigid certainties of arithmetic and the statistical regularities of probability, thereby teaching mathematicians an entirely new language for speaking about Section 1. The initial inquiry and the legacy of Hardy and Ramanujan. The paper commences its investigation by grounding its central question in the prior work of Godfrey Harold Hardy and Srinivasa Ramanujan. The key claim advanced in this introductory framing is that the Hardy-Ramanujan theorem of 1917, while fundamental, offers an incomplete picture of the arithmetic landscape. That theorem had established that the normal order of the function omega of n, representing the number of distinct prime factors of an integer n, is the logarithm of n. This means that for almost all integers, the value of omega of n is very close to this function. Erdös and Kac implicitly posit that knowing the average behavior is a starting point, with the more profound question concerning the nature of the deviations from this average. The evaluation of this initial claim reveals it as a masterful act of intellectual reframing. It repositions a celebrated result as a prelude to a deeper inquiry. The mechanism for this is a shift in perspective from a statement about central tendency to a question about distribution. The paper's opening argument is that understanding the full statistical structure of the values of omega of n provides a much richer description of the integers. The evidence for this claim is conceptual. It lies in the ambition to seek universal statistical laws within the domain of number theory. By asking how the values of omega of n are distributed around their mean, Erdös and Kac were essentially hypothesizing that the seemingly erratic placement of prime numbers gives rise to a globally regular and predictable pattern. This initial section's argument is coherent and powerful because it identifies a frontier of knowledge and proposes a clear, ambitious direction for exploration, effectively turning the conclusion of one great theorem into the premise of Section 2, the probabilistic heuristic and the central limit theorem analogy. The second major argumentative block of the paper introduces its core conceptual innovation, a heuristic bridge from number theory to probability theory, an idea largely credited to the intuition of Mark Kac. The central claim here is that the arithmetic function omega of n behaves analogously to a sum of independent random variables. The framework proposed to substantiate this is a thought experiment. One is asked to consider a set of simple random variables. Let us call them x sub p for each prime p. Each variable x sub p would take the value 1 if a randomly chosen integer is divisible by the prime p, and the value 0 otherwise. The sum of these variables, taken over all relevant primes, would closely resemble the function omega of n. The brilliance of this model lies in its elegant simplification. Evaluating this claim requires inspecting the strength of the analogy, the events of divisibility, by distinct primes, for instance by 2 and by 3, are indeed independent in a purely probabilistic sense over the infinite set of integers. The probability of an integer being divisible by 6 is 1/6, the product of 1/2 and 1/3. The paper's argument acknowledges that within a finite set of integers up to some large number n, these events possess slight correlations. The genius of the heuristic is its assertion that these correlations are asymptotically insignificant. The mechanism for translating this heuristic into a concrete mathematical prediction is the central limit theorem. This theorem states that the sum of a large number of independent and identically distributed random variables, where appropriately normalized, will be approximately normally distributed. By claiming that omega of n behaves like such a sum, Erdös and Kac were directly predicting that its distribution, when centered and scaled, must converge to the Gaussian curve. The assessment of this section's argument is that it provides a stunningly effective, albeit non-rigorous, blueprint for the formal proof that follows. It succeeds by importing a powerful explanatory tool from one domain into another, offering a clear and compelling reason to expect the emergence of the normal distribution. Section 3, the formal proof strategy and the method of moments. Having established the probabilistic intuition, the paper transitions to the formidable task of constructing a rigorous number-theoretic proof. The primary claim of this central, technical section is that the convergence of the distribution of omega of n to the normal distribution can be proven by demonstrating the convergence of its moments. The chosen methodology is the method of moments from probability theory. This method provides a clear criterion for convergence if the kth moment of a sequence of probability distributions converges to the kth moment of a known distribution for all k, then the distributions themselves converge. In this context, the goal becomes calculating the moments of the normalized function, which is the quantity formed by taking the number of distinct prime factors of an integer n, subtracting the logarithm of n, and dividing the result by the square root of the logarithm of n. The paper claims that the limiting values of these moments match precisely the moments of the standard normal distribution, which are 0 for all odd moments and a well-known sequence for the even moments. The evaluation of this claim hinges on the technical feasibility of these calculations. This is where the paper's argument reveals the profound contribution of Erdös. Computing these moments requires counting the number of integers up to n that have a specific number of prime factors with certain properties. This is a deep problem in analytic and combinatorial number theory. The paper outlines how this counting can be achieved using sophisticated tools, chief among them being the Brun sieve. The Brun sieve is a technique for estimating the size of sifted sets of integers, meaning sets from which multiples of certain primes have been removed. Its application here is the critical mechanism that allows the authors to manage the statistical dependencies between prime divisors. The sieve provides the necessary control over the error terms that arise from the simplifying assumption of independence. This section's argument is thus a tour de force of technical mastery, demonstrating that the probabilistic intuition of the previous section can be translated into the rigorous language of number theory and its most powerful enumerative techniques. The claim is validated by the successful execution of this complex computational program. Section 4, the management of error and the partitioning of primes. A crucial and subtle part of the argument concerns the precise management of error terms. The central claim here is that the cumulative effect of the statistical dependencies among prime divisors is asymptotically negligible. The primary mechanism for proving this is a clever partitioning of the set of prime numbers. Erdös and Kac divide the primes into two categories, small primes and large primes, relative to the upper bound n of the integers being considered. The argument proceeds by analyzing the contributions of each set to the function omega of n for the small primes. The paper demonstrates that their contribution to the moments of omega of n behaved almost exactly as predicted by the independent random variable model. The sieve methods are most effective here, providing sharp estimates that show the error terms diminishing as n grows. For the large primes, a different argument is employed. The paper shows that for a typical integer, the number of large prime factors is very small, therefore their contribution to the overall value of omega of n, and consequently to its statistical distribution, is minimal. The evaluation of this strategy reveals its deep insight into the structure of integers. The partitioning scheme effectively isolates the well-behaved, dominant part of the problem from a secondary, more erratic part, and then demonstrates the latter's ultimate insignificance in the limit. The logical coherence of the entire proof rests upon the strength of the bounds derived in this section. The evidence provided consists of a chain of inequalities and asymptotic estimates, each one carefully constructed to control the error introduced at each stage of the approximation. Assessing this part of the paper's internal claims requires appreciating the delicate analytic footwork involved. It is here that the argument solidifies, transforming a plausible heuristic into a mathematically sound theorem. The successful containment of all error terms confirms the robustness of the probabilistic model and validates the paper's central conclusion, Section 5 generalization, and the identification of a structural principle. In its concluding passages, the paper makes a powerful claim about the generality of its findings. It asserts that the phenomenon of normal distribution is a property of a wide class of arithmetical functions, extending far beyond the specific case of omega of n. The mechanism for this generalization is the identification of the underlying structural properties required for the result to hold. The authors state that the theorem applies to any strongly additive function, which is a function f such that f of a product of coprime integers and b is the sum of f of a and f of b, and f of a prime power is equal to f of the prime itself. They specify the necessary growth conditions on the values of such a function at prime numbers. Specifically, the sum of the function's values at prime should diverge, while the sum of the squares of its values should converge. When both are suitably normalized, the evaluation of this claim reveals it as perhaps the most profound aspect of the work. It elevates the result from a specific observation about one function to a meta-theorem about the statistical behavior of additive functions in general. This demonstrates that the Gaussian distribution arises as a deep structural consequence of the way integers are built multiplicatively from primes. The claim was prophetic. Later work, particularly the Kibelius-Shapiro theorem, would formalize and expand upon this very idea, creating a comprehensive framework for determining the statistical distribution of a vast array of arithmetical functions. The evidence for the paper's claim of generality is its correct identification of the essential analytic conditions. By pinpointing what properties of omega of n were truly necessary for the proof, Erdös and Keck abstracted a fundamental principle of arithmetic. The reception of this particular claim within the mathematical community was one of immense excitement, as it opened up a whole program of research to test the limits of this newfound principle. In conclusion, the 1940 paper by Paul Erdös and Mark Keck stands as a monument of mathematical synthesis, its claims validated at every turn by a fusion of probabilistic insight and number-theoretic power. The work's internal arguments, evaluated section by section, reveal a seamless logical progression from a brilliant heuristic analogy to a technically unassailable proof. The initial reframing of the Hardy-Ramanujan result posed the critical question of distribution. The probabilistic model provided a clear and compelling answer, predicting the emergence of the Gaussian law. The method of moments, powered by the technical machinery of sieve theory, provided the rigorous validation, with the careful partitioning of primes ensuring all error terms were controlled. Finally, the generalization of the result identified a universal statistical principle governing the additive structure of the integers. The enduring significance of the Erdös-Keck theorem resides in this complete and successful execution of its ambitious claims. It equipped number theory with a new and powerful lens, one that revealed a world of astonishing statistical regularity hidden within the discrete and seemingly chaotic realm of the integers. It did more than solve a problem, it created a field, demonstrating that by viewing the integers from a collective, probabilistic standpoint, one could uncover an order of profound depth and elegance.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.